Okay, guys. So the last topic of this section is rearrangements, and this is a very, very interesting and acute topic. You may not think that, but it is. So notice that if I want to add 1 plus 2 plus 3, I can add it in any way I want, like 1 plus 3 plus 2, or 2 plus 1 plus 3, or anything of this form, and the result will always come out the same. In other words, the addition is commutative. So the question becomes, what happens if I have infinite series, Cn, and say from whatever, 0 to infinity? And so this is a series C1 plus C2 plus C3 plus C4 plus etc. And let's suppose that the series converges, and it converges to some number, whatever, alpha. What will happen if I rearrange the series? What will happen if I say C5 plus C1 plus C100 plus etc.? The first question is, would the series necessarily converge? So I'm adding these numbers in any order, and if it would it converge to the same alpha? Okay. And there are two answers to this question as before. One of them is almost predictable. So before I start, let me talk about rearrangements, and let me try to uh, define it in any reasonable way. So one way to define it is about permutation. So sigma is a mapping from, say, natural numbers into natural numbers, which is 1 to 1 and onto. And I'm looking at the series sum of Cn and the sum of C sub sigma of n. So whatever sigma of n is, it's some number, and I'm adding these numbers in this particular order. Okay, Rudin doesn't go this way. He is doing something hopefully a little bit different. He is talking about the number Cn prime, which are equal to C and K. So it's one of those numbers uh, of C's, except it assign a different order once again, and he is looking at the series Cn prime. So this is like, you know, Cn1 plus Cn2 plus Cn3, and you go on like that. And so this number Cn1, Cn2, Cn3, they appears, each number is the same as those numbers C. They appear only once, and each one of them appears, and this will be the new series. And the question is, does this series necessarily converge or not? Let me check this. Well, the first question is, the first answer is kind of yes. And here is the theorem. And this theorem is very elementary, except you have to think about it a little bit, because if you're not used to dealing with those rearrangements, then it will take a little bit of time. Okay, so let me do with the first theorem. If the series Cn and from 0 to infinity converges absolutely, once again, this means it's a series Cn with absolute values and from 0 to infinity converges, then the series C prime of n, so this is this permutation, guys, also converges and to the same number. In other words, if the series converges absolutely, then you add the terms of the series in different order, and the resulting series would still converge to the same number. Okay, let me do a proof. And the proof is not very difficult, but you have to be a little bit conscious of this thing. Okay, so first of all, I know that the series Cn converges. And what I'm going to do next is I'm going to use Sn to denote the partial sums. for the series. All right. So what I also know is that the series Cn converges absolutely, which means that the remainder here, Cn n is greater or equal than some number n, converges to 0 as n tends to infinity. Okay. Moreover, I know that this thing have the properties that Cn Sn minus Sn, right? So this is less or equal than the sum of Cn plus Cn plus 1 plus etc. plus Cn. Remember, the little n is less than capital N, and this thing tend to 0. Okay, so here is the only trick to this proof, and it's not too difficult, but I think it needs a little bit of thought. So if you need to pause the video and think about it. So let me suppose that I have the series. So Sn prime will be the partial sums for the series Cn prime, and from 0 to infinity, and this is the sum of some C and K, right? K goes from 0 to infinity, where those numbers and K run through all of the natural numbers. Okay, so I'm going to start with this number n that I defined here. And what I want to do is I want to choose nk. So I want to choose k so large that the first n term of the series C1, etc., Cn appear among the terms Cn1, etc., Cnk. Okay, so let me pause it for a second and think about it. Look what's happening. I start out with this number C1, C2, C3, plus, etc. Okay, and then I'm going to rearrange them. So first there will be, say, C sub 100, and then there will be C sub 1,000, and then there will be a C1, and then there will be a C sub 10,000, and then will be a C2, or whatever. You see, I'm rearranging in an arbitrary fashion. And what I claim is that for some sufficiently large n sub k, so when n sub k is very, very large, it means that uh, among the numbers C sub n1, C sub n2, etc., C sub nk, all the numbers C1, etc., Cn appear. So for instance, in this case, let's say this is C sub a million, and if I choose nk to be a million, then the numbers C1 and C2 appear in them. And if I choose nk to be a billion, then the numbers C1, C2, C3, C10, up to C10 will appear among them. So if I choose sufficiently large nk, then all the numbers up to n will appear in it. Okay, so this is the only kind of point which is not difficult but requires a little bit of thinking. And once you thought about it really, really hard, you will quickly see that that means that if I look at Sn minus Sn sub k prime, these partial sums will in particular contain all these numbers C1, Cn, and they will cancel each other. And so this will be less or equal than the sum of C sub m. M is greater than n, and less than nk. And this will be less, and this will converge to 0 because what I have here is nothing else but the partial sums of Sn k minus Sn, and I know that this converges to zero. Well, not only that, but it also shows to me that the partial sums Sk prime minus Sn converge to zero as k and then tends to infinity. And what that means is that the partial sum Sk prime of the rearrangement and Sn converges to the same limit. Right? Which basically concludes the proof of this theorem. And I hope you kind of agree with me. Okay? Uh, so I don't know how to explain it any better, but I hope I said enough words for you to at least get a clue of what's going on. Okay, the really interesting part about it is the second part, and it's a very famous theorem of Riemann, and Riemann is one of the leading mathematicians of the 19th century. So it's a very famous theorem of Riemann that says something absolutely spectacular about rearrangements. And that will be the last topic in this particular chapter. So the theorem of Riemann says that let's suppose that I have the series Cn, which converges conditionally. So this time, the series do not converge absolutely. Uh, Now something spectacular happened. Pick any number you want. Let's say 7. Or, I don't know, e to the square root of 3 divided by 2 plus pi to the power 10. Whatever the number, or to the power 100. Whatever the number you want to pick, it's fine with me. There exists a rearrangement of those series such that, well, such that what? Such that this new rearrangement, sum of Cn prime, converges, and in fact converges precisely to that number, to e to the square root of 3 divided by 2 plus pi over 100. In other words, if I have the series of the form sum of minus 1 to the power n times 1 over n plus 1, remember we dealt with the series before, this is the series that converges conditionally. And whatever the number you give me, you can give me this particular number. I can rearrange the term of the series in such a way that the resulting thing, sum of minus 1 to the power nk, 1 over nk plus 1, where nk run through all integers n, but in some particular order according to k, the series will converge, and they will converge to that number, e to the square root of 3 divided by 2 plus pi to the power 100, or whatever. Okay, moreover, I can also rearrange the series so that the rearranged series, Cn prime, diverges. So the partial sums can tend to infinity, or can take to minus infinity, or Rudin states this theorem in a little bit more general way. So I will not prove it in his way. I will prove it in a little bit easier way. So pick any two numbers. Alpha 1 less than alpha 2. And remember, alpha 1 could conceivably be equal to minus infinity, and alpha 2 can conceivably be equal to plus infinity. Well, in that case, there exists a rearrangement of this series Cn prime such that the lim sup of the partial sums Sn prime is equal to alpha 2, including possibly infinity, and the lim inf of Sn prime is equal to alpha 1, including minus infinity. Okay, so to give you a little bit of a break, what I would like to do is I would like to do just this theorem about an arbitrary number alpha, and let me do it now. So this is a simplified version of a theorem in Rudin. Again, the Rudin theorem is a little bit better. So the theorem is that let sum of Cn converges conditionally, and let alpha be any number, including minus infinity, any number, or infinity. Oops. Then there exists a rearrangement of this series such that the new series converges to alpha, with an understanding is that if alpha is minus infinity, then the partial sum of the series converges to negative infinity, and if alpha is positive infinity, then the rearrangement of the series converges to positive infinity. Okay, and that's the theorem that I want to prove now, and this will be the last theorem of this chapter. So the way the proof goes is as follows. What Rudin does is he says, let's suppose that Pn is equal to Cn plus, with absolute value, plus Cn, so this is absolute value, divided by 2, and let's suppose that Qn is equal to absolute value of Cn minus Cn divided by 2. Okay, so this is kind of notation, and they may look stupid, but what do they mean? They mean that what happens, for instance, for Pn, if Cn is positive, in that case, Cn absolute value plus Cn is simply equal to 2Cn, right, divided by 2. This will give me, then the result will give me Cn. And if Cn is negative, okay, then the absolute value of Cn is minus Cn, and then you add to it Cn, and so the value will simply be 0. So again, Pn is equal to Cn if Cn is positive, and it is equal to 0 if Cn is negative. And then the same thing works for Qn, only in opposite order. So if Cn is positive, right, in that case, this is equal to 0. So 0 if Cn is positive, and this is equal to minus Cn if Cn is negative. In other words, what these numbers Pn and Qn do is Pn represent all the possible positive terms of the series Cn that I started out with. Qn represents minus all terms which are negative, which comes from the series Cn. Remember, there has to be infinitely many positive terms and infinitely many negative terms among those Cn's in order for the series to converge conditionally is not, and not absolutely. If there are only finitely many Cn's which are, say, negative, then the series would converge absolutely, because taking absolute values of Cn will not change most of the terms. All right. Okay. So now, claim 1. The sum of Pn. So this is the sum of positive terms here, and the sum of Qn, so this is the sum of absolute value of the negative terms, diverges. Well, is this obvious? Well, let's see. If this series both converge, then the difference would converge, and the series, if if this series both converge, then the sum would converge, and the sum of the series are nothing else but the sum of Cn absolute value, and so we know that this diverges, so it is not possible that both series converge. Okay, uh, so what will happen if, for instance, this series converge, let's see, converge, and this series diverge? Then again, I would look at the sum of Pn plus the sum of Qn. This converge, this diverge, and so this series will diverge with a minus sign, will diverge. And of course, the series with a minus sign is nothing else but the series with Cn, and we know that the series converges. So as a conclusion, we conclude that both series with Pn and Qn converges. And now we come to an absolutely terrific, very, very short, very, very quick idea. So I'm going to pick a number alpha, right? And what I'm going to do is I'm going to take P1 plus P2 plus etc. plus Pn, and I'm going to take n to be the least possible so that the sum of P1 plus P2 plus etc. plus Pn is greater than alpha. Well, what do I mean by that? First of all, can I always do it? Well, yeah, the sum of p's diverge, so they tend to infinity, so I can always get them to be greater than any possible number alpha. On the other hand, what I will know is that p1 plus etc. plus pn minus 1 is definitely less than alpha. Do you agree with me? And so my conclusion will be that the difference between uh, this sum and alpha will be Pn. So Pn, P plus 1, plus etc. plus Pn minus 1, right? This is less than alpha, and this is greater than alpha. So the difference between alpha and P1 plus etc. plus Pn is less than Pn. Okay. So now I'm going to take this particular sum, and I'm going to add to it the negatives of Qn, or Qm. And I'm going to add the skews to them, m here. And m is the least such that this sum will be less than alpha. Okay, and again, because q's diverge, so the sum of absolute values of q's tend to infinity, it means that if I subtract enough of them, I will get somewhere which is greater less than alpha. Okay, so this over here is a rearrangement of my series. When I take the first n positive terms first and the first m negative terms next and add them together. Okay, and so if you do this construction very, 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 very carefully, then the result will be that alpha minus this partial sums, right? Uh, and so this is a partial sums of P1 plus Pn minus Q1 minus etc. minus Qm. So the difference between those things will be less than the maximal value of the Pn and Qn. Now remember that the series with Pn and Qn's converge. They just converge conditionally, which means that the terms Pn and Qn tend to 0, and therefore alpha minus Sn prime converges to 0. So this is a remarkable, remarkable, remarkable theorem. Again, it's a theorem due to Riemann that, unlike absolutely convergent series, if I have series which converge conditionally, then I can always find the rearrangement that converge to any possible number alpha. For instance, alpha, I forgot what it was, e to the power of pi divided by square root of 2 minus 1 to the power of 100, whatever. So whatever number you pick, you can rearrange this series in such a way that the resulting series would converge. Okay, and that is the last theorem of this chapter. And so on Tuesday, I'm hoping to hear some questions from you about what we cover. And on Thursday, I'm going to give you a test. So not this coming Thursday, but the one after. And that will be a test. I haven't decided how to do it yet. So uh, I will have to make my decision later. Okay, bye.